This is the Lone Crater YouTube. We hope this video helps.
You begin by sealing gaps in math and tools. Master linear algebra topics like eigenvalues and tensor products because qubits behave as vectors. Once done, refresh complex numbers and probability. These explain amplitudes and measurement. Next, install Python and a quantum SDK such as Qiskit or Cirq and run a single qubit circuit to see state preparation and measurement. Make sure to write one short script that creates 0, applies a Hadamard, and measures to observe superposition statistics. You now expand from toy examples to meaningful experiments. Study gate sets, controlled operations, and how entanglement emerges with Bell pairs because that underpins quantum speedups. Then implement hallmark algorithms, Deutsch-Jozsa to grasp oracle structure, Grover for amplitude amplification, and basic phase estimation for eigenvalue problems. Once implemented, simulate noise models to understand decoherence, and run the same circuits on the smallest available hardware to compare ideal versus noisy outputs. That contrast teaches practical limitations. You complete the learning path by delivering a capstone project. Choose a variational algorithm or a tiny quantum chemistry problem to apply everything. Document each experiment, record fidelity and measurement statistics, and iterate while applying error mitigation methods because reproducibility accelerates insight. If something breaks, first isolate assumptions. Simplify the circuit to a 2-qubit test, verify qubit mapping and backend constraints, and rerun simulations. This focused debugging approach reveals whether errors stem from code, hardware, or theoretical understanding.
Thanks for watching. Consider subscribing if we helped you.